All right, guys, so I want to go back to a second example, but I want to bring up a topic that we've already talked about and just kind of look at it in more detail now. So imagine me getting a sample of gasoline in the laboratory. We said that these are probably 60 or 70, 80, 90 components in the thing, depending on the sources, depending on the type that we're getting. So very, very complicated mix. A perfect example of what standard addition is all about. And in the previous videos, we've constantly focused on benzene, and I want to do that again here as well. So let's say that we have benzene in the laboratory. We're going to make a standard addition set using benzene because that's how much we want to maybe pay attention to in the gasoline sample. We want to know, is it over the regulated limit or not, right? Okay, so here's another example of using standard addition and prepping samples. Now, this is going to be very familiar to the previous video with one minor change, and you'll see what that change is going to be in just a second. All right, so in the first one, we're going to have a blank. So that blank means nothing was added in at all, right? And we're going to assume that this is 25 milliliters now, just to change it up from the previous example. All right, in standard number 1, standard number 2, standard number 3, in the previous video, we mentioned that it's much better to use very small amounts of component that you're looking for. This way, across the board, for the most part, the solvent, which is the sample, can stay present in about the same amount. Okay. So in the first flask, we're going to add 0.5 microliters. In the second flask, we're going to add 1 microliter. And in the third flask, we're going to add 3 microliters. Now, 3 microliters of what? Well, it's 3 microliters of benzene. So benzene doesn't really come to us in a concentration. You know, in the previous example, we said, hey, we got PTFE and it's in 1,000 ppm. Well, what if we just use point blank benzene? We directly add that. What's the concentration of benzene? You can't really find that. There's not going to be a label. So this is one of those examples where we're going to have to use a liquid in order to make these samples with. And the liquid is going to have a density. And that density, of course, is grams per milliliter. Well, if I know the volume, and I do, 3 microliters, 1 microliter, a half of a microliter, I can calculate the gram of benzene that I'm putting into my solution. And from that, I can then spin off in any kind of concentration that I want. So with grams, I can convert that to moles and I can go into molarity, right? And with gram, I can go to milligram and I can talk about part per million. And I can go to microgram and I can talk about part per billion. I can use gram and use that directly, don't do anything with it at all, and talk about percentage. All of the concentration units that we've brought up this point in the course, I can relate this standard set to. Okay, so what concentration would this lab experiment like for me to report? Well, just because I want you to do a little bit of work, I want you to go to molarity. Okay, we're going to do one of these examples, follow through with the calculations and figure out how to do these because it seems like this is the one that people have the most problems with. I think once they get into gram, they feel pretty good about being able to convert it to milligram to get to ppm or microgram to get to ppb. But if they've got to do a little more work and get to molarity, that's where the problem happens. All right, so I know the first one's going to be pretty easy. This is going to be no molarity at all, right? That's my blank. I didn't add anything to it, so because of that, it's my 0. The first one, though, that's a half of a microliter. All right, so 0.5 microliters over 1. We're going to do this conversion together. And I'm going to do it old school. I'm not going to skip any steps. I'm going to kind of show you the proper way of going through it all. All right, so microliter on top, microliter on the bottom, and I need to go to liter. So microliter is 1 million in 1 liter. All right, and the next step, well, I'm in liter now. I need to get back out of there, so liter on the bottom. And I need to get to mil, because I eventually want gram, right? I need molarity, which needs moles, which need grams. That's the common thought flow here. So this is related with milliliter, so I need to get to milliliter first. So there's 1,000 milliliters in a liter. Well, milliliter on top, milliliter on the bottom. I now need to go to gram. So in order to do this, I need the density of benzene, right? And the whole concept behind this is because this benzene is a pure substance that we're using. It's not diluted. It's not in a solvent. It's full-blown benzene. The previous example was PTFE that had a part per billion concentration associated with it. That means a little bit of it was dissolved in a solvent. That's where this example is different. This is nothing dissolved in a solvent. Benzene is just benzene straight from the bottle, just like acetone is straight from the bottle. Methanol is straight from the bottle. Benzene straight from the bottle here. So if I add a half of a microliter, I want to know the actual amount that I have put into that flask. And I want to report that concentration in molarity. So I've got my microliter, converted it to liter. Converted it to mil, because density requires milliliters here, and that will allow me to go to gram. So I now need the density of benzene. So benzene's density is 0.876 grams per mil. So that means in this dimensional analysis step, in 1 milliliter, there's 0.876 grams. Okay, so if I stop this here, that will allow me to figure out the number of grams that's inside of that flask of benzene. Now, from this point, again, I can go into many different concentration units. I can convert my gram to milligram, look at the total volume that I've made to calculate part per million. I can take the gram, convert it to microgram, look at the volume that I've made, and convert that to parts per billion. I can take my gram and keep it as gram, divided by the volume in milliliter, and that will give me percentage. Or in this case, we need molarity. So we need to go one more step, and that's to convert my gram into mole. Okay, but I'm going to do that in a second step, just so you can kind of see the numbers and where they're going to go. So 0.5 microliter divided by 1 million. That will give me liters, times it by 1,000. That will give me milliliter, and then we're going to times that by 0.876, which will give me gram, 0.000438. Again, from this point, I can go in multiple directions, but we need to go into mole so we can get into molarity. So once I have my gram, I now can take the grams, and if I want to set it up dimensional analysis, that's perfectly fine. I've got no problems in that. Gram on top, gram on the bottom. Dimensional analysis didn't do anything to you. It still wants to be your friend, and we need to go to mole. All right, in order to go from gram to mole, we basically need the formula weight for benzene. And that's going to be 7811 grams per 1 mole. All right, so I'm going to take 0.000438, and then I'm going to divide that by 78.11. I hit enter, and I'm going to get a bunch of zeros out in front. 0.000056. So 5 zeros with a 56. Now that's the amount of benzene I have in the very first flask. And we said that these flasks that we're going to use for this example, they're 25 milliliters in total, right? So if I had to calculate molarity, keep in mind molarity's moles per liter. There's my mole. I'm going to divide it by liters that I have put it in. Well, 25 milliliters is 0.025. So I'm going to take that number, divide by 0.025, hit enter, and I'm going to get 0.000224. 0.000224. Super low concentration. This is kind of what we like to see in standard addition, and this is why we've talked about it before, right? We like to have very small additions into the sample, and we want to see how the signal corresponds and changes to those very small additions. We have a very small concentration because we've added a very small addition to the flask. So from this point, I would do the same thing for the 1 microliter and the same thing for the 3 microliter. So the numbers that would change up on your screen that you're seeing now are these right here. So instead of a half, in the next example, I would do a 1. 1 divided by 1,000,000 times 1,000 times 0.876 to get gram, divided by 78.11 to get mole, and then divide by 0.025 to get molarity. And then I would do the same thing with number 3. I've added 3 microliters of a pure benzene sample. So I would put a 3 into this space, divided by 1,000,000 times 1,000 times 0.876, divided by 7811, and then divided by 0.025. And that will give me the concentration and molarity for spot number 2 and spot number 3. So here are the concentrations for each one that I've done. So I plugged the 1 in first, and I got a concentration of 0.000449. And then I've plugged in the 3, and I got a concentration of 0.00135. Now, before I go any further, I just want you to kind of step back, use some common sense, and figure out, does that really make sense or not? And the answer is yeah. Here's the shortcut, people. Here's a half, and my concentration was 0.00224. Well, if I double that and go to a 1, my concentration should double. And it does. 0.00224 to 0.00449. And then if I go from 1 to 3, that's 3 times as much. So my concentration should go 3 times as much. And it does. 0.000449 times 3 is 0.00135. So a very quick way that we can double check our math to make sure that everything worked out in the end. Look at your volumes. Your concentrations should go up proportionally, right? Okay, so there are the concentrations in molarity from the standard additions that I have ran. Now, my next job is to go into a room, go to a piece of equipment, go to some type of procedure, and get some signal data from these standards that I have made. So I'm going to end up running these probably on a gas chromatograph, a GC unit, and the GC unit could be paired up with a mass spectrometer. Those are the things that you'll learn about in a completely different course. But this machine is going to give me some signals. And those signals I'm going to write down. So I've got my 0, which is my blank, and then my 0.000224, and my 0.000449, and my 0.00135. So here is my concentration in molarity, and then my signal. So with the power of the camera, ta-da! Here are my absorbance values: 0.141, 0.167, 0.189, and 0.298. All right, so after I've ran these samples in a lab, I would go back to some kind of computer software, or maybe in that instrument software. Who knows? Maybe it will automatically do it for me. But I need to make a standard calibration curve. So I'm going to open up Excel, and I'm going to type in the concentrations over here to the side: 000224, 000449, 00134. And these are the signal values that are associated with those numbers. Keep in mind that this is molarity, and this is just the signal. All right, just like before with any other calibration curve, I'm going to group them. I'm going to go to Insert. I'm going to go to Scatter, and I'm going to plot the points only. And there's my graph. All right, well, with this graph, we want to add a trend line just like we've always done. So click the data set. Over here to the side, when you click that data set, you're going to right click and add trend line. Scroll down to the bottom, display the R squared, display the equation. And there it is. Looks pretty linear. 9989, which rounds off to 999. So it looks pretty good. But I want to go backward because this is standard edition, right? I know it's standard edition because my blank that had nothing in it had a signal, and it was a pretty large signal, right? And I need to figure out how much was present in that sample that was brought in. Well, I need to extrapolate the data backward, just like we did in the previous example. So it looks like this is 0.0002. That's the unit which is spanning right there. Well, if I go that much to the left, that line's still not going to cross the x-axis. If I go on another unit to 0.0004, maybe on the negative side, still really hasn't crossed. It's probably not going to cross until it's way out here over to the left. Well, again, look at these units, right? That's what we keep talking about. Look at those units. Those units will help you determine the backward forecast for this linear regression line. So down here under backward, I know I'm not going to start off with 100 because these units are OOOs. So that would be stupid. So what I want to do is that I want to maybe start off with 0.001 just to see what happens, right? And when I do that, it looks like it hasn't crossed the x-axis yet, but it's getting really close. So I need to span this on out a little bit. Well, look, Excel already put in an 0015 for me. So why not just go on out to that point? Let the line keep on a-trucking. And there we go. There's the 00 point of origin right there. And if I go over to the left, I'm going to see that that line now crosses the x-axis. And that's good. That's what I want to see graphically on a software system like this. So this will give me an eyeball. It will give me an estimate of where this is going to happen. 001 and 0015, it looks like it's in between those two numbers. So I know that when I solve for this equation, well, I know the number I should be expecting. If I don't get that number, I've solved the equation the wrong way. Okay, so I'm going to take this graph now. And again, this is 0.00. We want to know where the line crosses the x-axis, which means y has to be 0. Y cannot be up. Y cannot be down. Y has to be on the 0 mark. So I'm going to plug 0 in for y and solve for x. So there's the equation that was from the Excel. We said y has to be 0. And we want to solve for the x to figure out where it crosses the x-axis. That represents concentration, right? So I'm going to bring up the calculator, going to solve this just like before. 0 minus 0.1396, hit equal. That gives me a negative number. And then to solve for x, we divide by 117.47. And I hit enter. And this gives me a concentration with a negative number. But that's okay. We pretend like the negative is not there. And it looks like the concentration in this sample would be 0.00119. And that is in terms of molarity. Okay, well, here's the thing. Molarity's great and all, but these standards could be enforceable with a different unit. And in this case, it is percentage. I'm not going to go any further with the example, but just be prepared to be able to convert again between units at the end of these problems. That's really what this class is all about. So once I get molarity, am I comfortable to understand that that is also known as moles per liter? So can I take this molarity number and can I convert that to part per million? Change this mole to milligram, and look, I've got part per million. Can I convert that number to microgram? And if I can, then I've got part per billion. Can I convert that to gram? And if I do, and I convert this to 1,000 mils at the bottom, that's equivalent to 1,000 grams, then all of a sudden I've got percentage that I can report as well. So once you get one unit, you can convert between all of them. Just be comfortable doing that. So this is how we have solved another standard addition problem. We did it graphically. We thought about the process of making the standards. What did we use? How do we solve for those concentrations? And notice how it was different than the previous example. In the first example that we did, we gave you an amount in volume, and that was a concentration, parts per billion. So we used a certain amount of that, and we diluted it in a volumetric flask. That's why we had to use CV equals CV. In this example, what we did is that we took really a pure substance. It wasn't diluted. It wasn't in a solvent. It was straight from the chemical reagent jug. That's how this one was different. So that's why we did not have to use this whole dilution step in the very beginning. We were actually able to take the volume and we used the density in order to get gram, which we then changed into another concentration unit. In this example, it was molarity, but it could have been ppb, ppm, percentage, or anything else that comes along with it. So just be comfortable with that concept. You've got to think about what you're doing, how you're preparing those standards, and how you can get a concentration from them. And I think that if you can do either one of these examples, right? If you can do both, that's great. But I think if you can do either one, you're pretty much already there. You just need an extra little push to go off in the other direction to kind of make those connections and make those links together between the example problems. All right, so that's where this example is going to stop. We have solved for our benzene concentration of our sample. It's right up here at the top. So that was great. That's what the problem was after. But you know, there's ways to do standard addition that doesn't require a graph. We keep using Excel. And I'll start off with this because I think people are more comfortable with it. You've done calibration curves this whole time. We've talked about calibration curves in the previous module. You're very comfortable with Excel and plotting data. And to me, graphically, standard addition just follows suit with that. But you do not need to do it graphically, believe it or not. You just need a little bit more math. So in the upcoming videos, what we're going to do is that we're going to turn our focus and we're going to look at standard addition problems and we're going to solve them, but we're not going to solve them with a graph. We're going to solve them with algebra equations instead. So no more Excel. Some of you might celebrate. Some of you might dread what's coming up.